The Solar Orbiter spacecraft has captured footage of a switchback, a sun reversal in the sun's magnetic field that traces out an elongated S shape. This is the first time a switchback has ever been directly observed, and the discovery provides clues as to how switchbacks form and how they may heat up and accelerate the solar wind. The finding was published in a letter to the Astrophysical Journal in September 2022 by Daniele Talloni and collaborators. The sun is driven by magnetic activity. Magnetic field lines twist and tangle, creating everything from seemingly quiescent sunspots to violent coronal mass ejections. Over a roughly 11-year period, the sun goes from being relatively quiet, with little to no activity, to an extremely active state with several major storms erupting every day. But even while it's quiet, the sun emits a continuous stream of charged particles called the solar wind. These wind particles are a plasma of electrons, protons, and various atomic nuclei. The particles follow the sun's magnetic field lines, many of which are open to interplanetary space. These open lines form what are called coronal holes through which the so-called fast wind escapes. Now, by fast, we're talking around 750 kilometers per second. And that works out to about 2.7 million kilometers per hour. But there's also a dense, slow wind as well that ranges from between 300 to 500 kilometers per second. So that's upwards of about 1.9 million kilometers per hour. The slow wind appears to originate somewhere above closed magnetic field lines called coronal loops. Charged particles get trapped in these loop lines, allowing us to effectively see the magnetic field. It's kind of like the way iron filings line up and trace out a bar magnet's magnetic field. When these closed field lines get extremely tangled or stretched, they break apart and reconnect. As the lines reconnect, the stored magnetic energy heats and accelerates the particles, typically very explosively. The equivalent of about 1 million hydrogen bombs of energy is unleashed in a matter of minutes. The result is an explosive flare or even a coronal mass ejection. But while the loops are still intact, they hold on to most of the particles, and those that do manage to escape aren't quite as energized or superheated, hence they are thought to form the slow wind. Much of these basic properties of loops, open field lines, and their respective slow and fast winds were well understood since the 1950s. But in the 1970s, the first hints of sudden reversals in parts of the magnetic field were recorded by the Helios 1 and 2 spacecraft. And these were among the first spacecraft designed to study the sun from as close as possible at the time. Their orbits took them to within 0.3 astronomical units, so well inside Mercury's orbit. In the 1990s, the Ulysses spacecraft recorded additional reversals, this time from distances beyond Earth's orbit. This quickly led to an hypothesis that perhaps the reversals were forming somewhere closer to the sun and maybe propagating outward, kind of like a wave on a snapped rope. In 2018, the Parker Solar Probe made its first of a series of increasingly closer flybys of the sun. Parker is designed to eventually close to within 0.05 AU. It does this by using gravity assists from Venus to drop in closer and closer to the sun with each flyby of the planet. But even during its first flyby in November 2018, Parker detected many sudden reversals of the magnetic field during its very first perihelion. The durations of the reversals ranged from just a few seconds to tens of minutes. During those events, the fields reversed by nearly 180 degrees before reversing back to their original direction. The reversals were dubbed switchbacks, and Parker essentially confirmed that switchbacks were in fact much more numerous close to the sun, and therefore were likely propagating outward where they could later be detected by more distant spacecraft. But how exactly do these switchbacks form in the first place? Well, astronomers are very good at coming up with explanations, and as a matter of fact, the less data they have, the more explanations they're able to come up with. Since the sun rotates, its outstretched field lines fan out in a kind of spiral structure. So, one idea is that maybe a kind of velocity shear would pinch several field lines back onto themselves. In some cases, the lines would reconnect and flare, while in others, they just form an S shape and produce a switchback. Another idea is that maybe there was some form of turbulence in the solar wind that temporarily bends the field lines back on themselves, creating switchbacks in the process. Still, another idea put forward by Fisk and Casper in 2020 suggested that switchbacks could form as a result of magnetic interchange reconnection. The idea went something like this. When an open magnetic field line is dragged against a large coronal loop, a reconnection event is triggered called an interchange reconnection. And this forms a kink in the open line. The original loop shrinks and the open line jumps across the sun's surface. Just like cracking a whip, the kink propagates out from the surface as a switchback. In 2020, Gary Zank and collaborators published a theory that expanded and refined on the interchange reconnection idea. It operates on the fact that the field lines are typically bunched together and emerge from the sun's surface through sunspots. In this revised model, the open field line trips against a bunch of closed loops. The outermost open line snaps onto the closed loop and undergoes an interchange reconnection event. Meanwhile, a new, smaller closed loop forms in between the two fields. As the outer S structure recoils, it launches a pair of switchbacks, one propagating upward and the other downward toward the sun's surface. But while that's happening, a second interchange reconnection event occurs and will produce a subsequent set of switchbacks that propagate up and down as before. The process repeats until the magnetic flux from either of the regions is exhausted, or if random motions of the underlying sunspots pull the fields apart. Of course, the real model isn't a set of cartoons, but rather a series of equations Zank derived to describe the events taking place. This model explains the outward propagation of the switchbacks and also explains why Parker was able to detect so many of them in rapid succession. But without any direct observations of a switchback in action, there was really no way to know just how robust this model was. But that changed in March 2022 when Solar Orbiter was about 1 day from its closest pass to the Sun. That allowed Solar Orbiter to observe the Sun's corona in visible light using its METIS coronagraph. And this is a device that blocks out the Sun to reveal the corona, which is about 1/1,000,000th as bright as the Sun's surface. Now at first, there's nothing that seems particularly special about this image, but when astronomers process the image to bring out smaller structures, an elongated S-shaped feature emerged. And this really looked an awful lot like the theorized switchbacks. Moreover, this feature was seen in several different reprocessing of the image using different algorithms. And that tells us that the feature is real and not some kind of artifact of the image processing. At the same time, Solar Observer used its extreme ultraviolet imager to image the sun's surface at the same time as METIS imaged the corona. Sure enough, the switchback feature was located almost directly above an active region, just as expected from the model. The METIS observations lasted 41 minutes, during which 120 frames were imaged. That allowed the team to watch the switchbacks form and propagate. In fact, one seemed to propagate forward while the other stretched backward. Again, consistent with the forward-backward motion of Zank's theory. The feature moved at around 80 kilometers per second. And that's much slower than the surrounding plasma seen in the METIS imagery. That's also expected because the switchback is coming from an active region that has not yet released all of its stored energy. So any wind emerging through the switchback ought to be traveling slower relative to the fast-moving solar wind surrounding it. Now, to further test the theory, the team created a computer model of the structure before it started to propagate. And then they allowed the structure to evolve according to the equations in Zank's theory. Now, the model wasn't super complete. I would imagine that it would require some supercomputer time to really model every particle through every step of the event. This was probably a desktop PC model, so it wasn't going to reproduce every single feature in the structure. But it did stretch out in pretty much the same way as the actual structures did. And this suggests that the interchange reconnection is very likely the mechanism that is in fact launching switchbacks. It isn't random turbulence, doesn't appear to be wind shear of any kind. It's interchange reconnection, baby. Now, the switchbacks themselves do not explain the origin of the slow solar wind. But in 2021, Zank and colleagues showed that the same interchange reconnection mechanism that launches switchbacks can, in other circumstances, heat coronal particles and generate the slow wind. Solar orbiters' observations don't go quite that far, at least not yet. But for now, they are showing that interchange reconnection seems to be able to produce switchbacks, and that alone is a huge step forward. Next would be to observe multiple switchbacks that propagate in succession as predicted by Zank's theory. And that's something solar orbiters should be able to spot in future orbits. Not only that, but the Parker Solar Probe is going to close to within 9.2 million kilometers of the Sun in March and June of 2023, and then drop to 7.9 million kilometers after its flyby of Venus in August. And that's just in 2023. Parker's closest flybys will begin at the end of 2024 when it comes to within less than 7 million kilometers from the Sun. Meanwhile, the solar orbiter will start to climb to higher orbital inclinations and eventually take the first images of the Sun's poles. And that's going to flesh out a lot more of our understanding of our home star. My thanks as always to my Patreon supporters for helping to keep Launchpad Astronomy going, and if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.